My name's John Adler, and I'm with NEON. We're a project that's funded by the National Science Foundation. Right now, we are operated by Battelle, and I work on the plane that you're going to hear about, and you can kind of see it on the right side of this picture here. And we're going to talk about our main largest instrument, which has 426 channels. Okay. And we're incorporating it into GEE, Google Earth Engine. And I want to highlight the importance of this is that normally you think of GEE as like Landsat, MODIS, this type of data, which is somewhere between 4 and maybe 30 channels, right? And so this is going to bring 426 channels for folks to do some analysis. So where NEON came from, the National Research Council back in 2001 started looking at climate change and how is this going to affect our ecosystems? And so they came up with some key questions. So, how is the climate change going to adapt to our ecosystem? How is it going to change there? How is our human impact, right? Land use, how is that going to change the ecosystem? Also, what about the species, the living species, how are they going to change? And so to answer some of these questions, came up with the key data products that we need to put out. So you're going to see how many we do. So phenology, hydrology, etc. And this isn't just for scientific folk, okay? This is for the public also, which is nice about the GEE platform, because you can come in and do your own analysis using our data, as well as students, educators, and others. NEON data has always been free and open data so that people can use it from around the world. Another key feature is a standardized framework. So the data that they're picking up is going to be consistently collected across the nation. Okay, so instead of having individual research projects which your data is collected differently, it's all going to be the same. And the data interoperability. And we're seeing this is a nice feature with GEE because we're able to pull our data, and using that metadata, which is interoperable, the data of data, is being successfully pulled into Google Earth Engine. And you're going to see examples here of 5 of our sites that were pulled in. So the National Ecological Observatory Network is a 30-year project. So this is long-term. So you're thinking kind of like Landsat in the 70s when it came out. Who knew what the uses were going to be? So this is kind of where we're thinking with NEON. You're going to be using this data, 30-year project, right? Continental scale. And what does this look like? So the U.S. is split up into 20 ecological domains. And these are areas that have similar characteristics. You can see these are highlighted by the blue lines. So within these 20 eco-domains, we call them, we have 81 field sites throughout where we're going to grab data, and I'll explain to you how we do that, of which 47 of those are what we call terrestrial data sites. So this is land-based, you think dirt type of sites, and 34 aquatic, and we're thinking wetlands, estuaries, places like that. So 180 data products are what we're putting out currently. So CO2 measurements, down to some of the other things I talked about earlier. How do we do this, right? So we have 3 major ways. So automated instrument systems, AIS, we're thinking towers, okay? We're taking automated systems, so humidity, temperature, pressure, winds, 3D winds, as well as some soil measurements also. So this type of data is automatically being taken in and archived. Then there's observational sampling. So this is in situ. You can see there's folks in the field here. So they're doing everything from species counts, so how many insect types or small mammals, etc. And these are over like tens of meters square plots throughout the sites that you saw, the 81 sites. Then there's what I'm on is the observation platform, and this is the remote sensing side of the house. And we are able then to fly over 100 square kilometer box that we put over these sites. So we had the in situ folks that were picking up the data on the tens of square meters. Then we have our observational platform, which is picking up 100 square kilometers. And this is going to lead for scaling up to overhead satellite type data that can then be used over these next 30 years. The platform itself has 3 major instruments. Okay, we have an RGB camera, red, green, and blue, so traditional camera that we're used to. We have a LiDAR system, which is throwing a laser beam down through the canopy, and then we have the imaging spectrometer, which is what this talk is about. A little bit more on the camera sensor itself. So this gives us situational awareness. So it's 10 centimeter resolution on the ground. So as we're looking at our LiDAR data, our spectrometer data, we can have some kind of situational awareness of what we're looking at by using this digital camera sensor. Now these photos are then aggregated and put into a mosaic, which is uploaded into GEE. Our LiDAR system is just past the visible into the infrared, and it has two functional characteristics. There's the standard LiDAR that you're thinking of, which is discrete. It comes down, bounces off the surface of the trees or a building or something, or it can penetrate through the canopy, bounce off the bottom of the ground, okay? And so with those different returns, we can have different products, which we'll talk about. Also, there's a waveform component. So this is where the LiDAR is coming down. It's actually giving you the shape of perhaps the tree crown size. And you can see in the red line there, it's kind of giving you more of the features available. But I want to highlight that this LiDAR data, XYZ data, we normally think of LAS files, is not going to be put on Google Earth Engine. It's the products derived. So the canopy height model, the digital surface model, so that first returns off the top, the ground return, and then if we subtract those two, we get the height of the canopy and tree. So that's the type of product which will be in GEE. So now the main feature here is the imaging spectrometer. As I mentioned, there's 426 color channels in here. So it's going from just into the ultraviolet all the way through past the infrared to 2500 nanometers. You can see kind of the color slides here. There's a couple of white areas, little valleys. This is where the atmosphere is actually absorbing that light. So we're not using that data in a couple of the atmospheric walls is what we kind of figured. That you kind of see it on the data cube. Those black lines are where it's being atmospherically absorbed. Okay. Now these channels are each 5 nanometers wide. So across this 400 to 2500, we've got these 426 bins, 5 nanometers wide, that's going to be put into the Google Earth Engine. Here's a quick example of what it looks like. You can see the 100 square kilometer box that we're flying. You can kind of see the north-south lines as we fly for the BRDF. And then if we zoom in into this little lake area, you can see in this case we had some calibration tarps that were down on the ground. And this is just a notional example of what you would get from the spectrometer. And you can see, depending which pixel you pick, you could have a reflectivity of grasses or of different tree types. And with this hyperspectral data, then we can break out to see and do some differentiation, which Shashi will show here in a second. For the products like leaf area index, so we take a couple of those bands. You can see here 850 and 650 nanometers. We do some math and we come up with a SAVI, right? The soil adjusted vegetation index. And then we can run that into another product, so the leaf area index, which is basically giving us almost like the thickness of how many leaves are there, so that we can do some further analysis. So these are some of the products that you'll come out. On the water side of the house, moisture stress index, you would grab different bands of those 426. And with Google Earth Engine, you're going to be able to do these on your own because all 426 will be available to you. Here's a quick picture in Kansas. So this is domain 6, and you can see our 100 square meter box. The blue line is kind of showing where the tower and those plots are that we were talking about, and then we're flying around the areas. And if we were to click on just one pixel, then up shows those 426 bands. And so we have that time domain component too. So 2018, and you can see the red edge coming up around 700 nanometers. Then the noise area in there are the atmospheric bands. And so with this, we're going to turn it over to Shashi, who's going to show you how to actually do this within the Google Earth Engine.
Well, so nice to see all of you here at the Google booth this morning. I'm Shashi Konduri, a remote sensing scientist working for the Airborne Observation Platform Group of the National Ecological Observatory Network, or NEON. And today I'll be talking about NEON's airborne remote sensing data that's currently available on the Google Earth Engine platform. So the goal of this demo is to look at how to access NEON's airborne remote sensing data in the Earth Engine platform. And then we're going to look at a simple example on how to combine different NEON data sets namely the plot level data for plant species type, as well as the remote sensing data comprising of hyperspectral imagery and the LiDAR-derived canopy height models to create a map of plant species type for a particular neon site. And just FYI, all the code that I'll be showing today is already uploaded on the Neon website as part of a tutorial series. So please don't worry about following each and every line of code or syntax. Neon generates several tens of terabytes of airborne remote sensing data every year. And they make it available to the public as 29 different data products collected over several sites spread across the US. Users can download all of the Neon airborne remote sensing data in three different ways. First, you could go to the Neon data portal, which is data.neonscience.org, and there's a whole bunch of filters that you can select, and you can manually download all of that data onto your machine. The second way would be to use the Neon API. So using just a few lines of code in R or Python, you can automatically download all of that data. And now users can also find the airborne remote sensing data on the Earth Engine platform. So this slide provides a quick summary of what all remote sensing data is available on the Earth Engine platform. There are three image collections. First is the surface directional reflectance, which is basically the hyperspectral imagery that John talked about. It contains 426 bands at 1 meter spatial resolution. You'll also find an image collection for the LiDAR-derived rasters, which is the digital terrain model, digital surface model, or the canopy height model. All of them also available at 1 meter resolution. And third, you'll also find the camera-derived RGB imagery. Neon currently has a 10 terabyte storage limit on the Google Earth Engine. So our data, the remote sensing data, is currently restricted to 5 sites, as shown here on the map, and with about 2 to 4 years of data per site. And now I'll quickly move on to the demo part. This is a simple script which shows how to import Neon's remote sensing data in Earth Engine. So users can simply write this line of code, ee.imageCollection, and then within quotes, projects/neon/ the name of the product or the product ID. So depending on whether you want to import the hyperspectral data or LiDAR-derived rasters or RGB, you would specify a different product ID here. If you type Neon at this point, you wouldn't find the data available because it's not up on the data catalog. So I just wanted to point that out. So the only way to access would be to use this line of code and then get access to that. Moving on. So once you import or ingest these data sets as import records, you can click on this link for more description on the data. So this provides a paragraph of information about what this data product is all about. But if you're more interested to know how we collected the data or what all processing went into creating those data products, we highly recommend you go through the algorithm theoretical basis document or the ATBD documents, which are uploaded on the Neon data portal. So this image collection contains several images in this case. So this is a hyperspectral image collection. You'll see that there are 12 images, and you'll have, we provide more information about each image here. And then similarly, you could go to the image collection for LiDAR derived. And again, it's going to hopefully show up the individual elements of that collection as well. If you're not interested in looking at or ingesting the whole collection, but looking at just one image, you can do that as well. And here in this visualization, we are showing one particular image for the Talladega Forest in Alabama. And this was collected in the year 2017. So this has 426 bands. So if you look at it, on the right side, there's an inspector tool. If you click anywhere on this image, you'll see that it shows up the hyperspectral imagery in the Earth Engine platform. Although it's not very clear here, the x-axis consists of 426 bands, and the y-axis shows the reflectance value for each of those bands. And you'll notice that there are a few bands in the middle where the reflectance values are like crazy high. So this region of the spectrum is affected by the water vapor absorption. So users are we highly recommend everyone to drop these bands before you do any analysis with it. Yeah, that's about it for this script. Then moving on to the next one. Here we're going to write a simple script to extract RGB bands and calculate NDVI from our hyperspectral image collection. So I'll simply show the visualization here. So this here is a RGB mosaic for a different site. So this is the Santa Rita experimental range site, which is, to my knowledge, probably the biggest neon site of all the 81 sites we have, spans several hundred square kilometers. And if you zoom in, you should be able to see that this is a really high res image, 1 meter resolution, and that you should be able to delineate individual tree crowns uh, yeah, in this imagery. And it's not just about creating an image for one particular year. You should be able to see a time series of data. So you can toggle data for 2017, 2018, 2019, and so on. So you can do a time series analysis using these image. And similarly, you can also calculate your NDVIs and other vegetation indices as well. I think the servers are running a little slow today. That's fine. We can move forward now. Similarly, you can also extract the LiDAR-derived rasters. In this case, we're going to look at the canopy height models. So this is we used a grayscale palette here. So each pixel in this image is also 1 meter resolution, and it will show you information about the canopy height at each pixel. And one good thing about dealing with canopy height models is you can look at the impact of environmental stressors like wildfires or hurricanes on the structure of the vegetation, and you can create difference maps between the canopy height models collected from different years. So this is one such difference map. So the green represents the areas where you see an increase in the canopy height, and red represents areas with a decline in canopy heights. And finally, and this is the most fun part of the presentation, which is a demo which shows how users can combine different neon data sets. Before I do that, let me switch back to my slides. So in this demo, we are going to perform vegetation classification using a machine learning model, in this case, random forest, for the CLBJ site in Texas. So there are two components here, the field data component and the remote sensing data component, both of which are now available on the Earth Engine platform. NEON has an in-house terrestrial observation sampling group, which consists of field ecologists who go out and visit several sites and collect field data for various ecological parameters. So for the year 2017, for the CLBJ site, our team collected 344 plant species observations for 7 species as listed here. And then they also collected GPS coordinates for those plots. For the remote sensing data part of it, we already have looked at our canopy height models and the hyperspectral imagery for 2017. So the goal of this exercise is to combine the canopy height model raster and the hyperspectral imagery raster and use them as inputs to a machine learning model, which in this case is the random forest model. And the goal of this modeling exercise is to predict plant species type. And we're going to take help of the field data for that. Now let me go back to my Earth Engine code. And this is probably the most critical line in this code, which is where we are importing our plot level data. So you can do that using ee.featureCollection feature/neon/AOP neon plots, and then the product ID here. And then you can also click on the import record to just get an idea of how this data looks like. So this is a tabular data. And if you scroll down, you'll notice that there are 374 rows, which is 374 observations of plant species type. And then you'll find information about the easting and northing. So that's the coordinates of each side of each plot. And then canopy height parameters measured in those plots. But for this modeling exercise, what we are really interested in is the taxon ID. So these are the 4-letter IDs which specify the plant species type. And this is what we expect the random forest model to predict. So in the interest of time, I won't go over the code because it's already available on the tutorials, but we're just going to look at quickly the results. So these are the sites where our terrestrial observation sampling group went and collected plot level data for those 10 classes. And if you use the random forest model, you'll be able to see that now we can create a map of plant species type for the whole CLBJ site. So this is a 10 by 10 box over which our remote sensing team collected our data, and so this was just a quick demonstration of capability here. Um, so switching back to my slides now, we'll be presenting similar stuff tomorrow at our poster. This will be tomorrow morning. Either me or John will be at our poster. So if you have any questions, please feel free to stop by. We'll be happy to answer your questions. Um, and one quick thing I wanted to point out is Neon invests a lot of time and effort into creating training and education materials. So please feel free to visit neonscience.org/resources/learning hub, and you'll find information about upcoming workshops and courses. And these could be half-day workshops to 3-day workshops, which provide information about how to access and work with Neon data. Also, all of Neon's code is open source, so you can visit our GitHub repository and get access to all the code there. And lastly, Neon also creates some self-paced tutorials. So these could be as short as 15 minutes to an hour. You can look at the different topics, or you can even choose the programming language of your choice and look at tutorials for that. And last but not the least, if you have any questions, please visit neonscience.org. And if you scroll down to the bottom of the page, there's a contact us tab. So fill in all the details, and one of the field experts should get back to you in less than a week. And I'll hand it back to John now.
And we also wanted to just highlight some of the science that has come out. So we have over 100 publications, that are using this data. Here's an example of functional traits, and you can see some of those outputs that we were talking about, some of those products, nitrogen index, chlorophyll. Another one that's more about what Shashi was talking about was a researcher team was using neural networks to look at identifying tree species using the hyperspectral imagery. And so on the Google Earth Engine, again, we're uploading aspects of the data. So you've got the 426 bands and you have LiDAR product, okay? But if you do need the actual raw data, you can still go, as Shashi had said, to our innate site and get the different level 1, level 2, level 3, or 4 data that you need there. And lastly, I just want to mention that in summary, so we have 5 sample sites, as we explained, but we're looking forward to putting up all of Neon's data in here, so, and throughout the time domain too. So in theory, this could happen in a fairly quick manner, and once that metadata is quality controlled, we will be able to search for it like you do with Landsat and MODIS. And so that's what we're looking forward to, is getting all the data into here, and then anyone across the world can be using Neon data.